Welcome to Part 10, Modeling Exponential Decline. Thus far, we've used exponential growth to model coronavirus cases. While exponential growth works somewhat well in the short term, and it does follow the shape of the curve when the underlying curve has actual exponential growth, it is not viable in the long term because all exponential growth models go off to infinity, and coronavirus curves are clearly capped by the world's population, and what tends to happen to them is that they go from exponential growth into exponential decline. So we'll see this with some data from Italy over here. So let's go ahead and plot this. So this is cases from Italy from about the middle of March all the way to the very beginning of June. And you can see that this is clearly not exponential growth. It looks fairly linear in the beginning over here, and then as we move on into April and especially in May, the number of new cases per day is getting less and less, and this is the cumulative curve. So what it's appearing that it's growing at a slower and slower rate. So the exponential growth model is not appropriate during this segment of the coronaviruses in Italy, and this is typical of what happens for many coronavirus waves. There is an exponential growth period, and then followed by an exponential decline period. Okay, so let's go ahead and try to fit our simple exponential continuous model in this case to this curve. So it should not fit, and when we run it, we have our predict all over here, so it's very simple. We just give it the model, and we just give it the bounds and a starting guess. And here we say to use April 10th as the very last date, and you can tell our exponential growth, it has to be shaped like this, concave up, and it just won't match the shape of the underlying curve, and so it doesn't really have a good chance at fitting it. So we need to use a different model, and we need to use a model that has some sort of exponential decline. Now there's a couple different types of exponential decline. The one that we've seen with our current model is called decreasing exponential decline. So the decreasing stands for the direction of the line, so in this case going down, and it's declining because it's going down at a slower and slower rate as the x values move on. So this is when b is less than 1. So over here we have b less than 1. And this is our simple exponential right there. Now, a different formulation of this is increasing exponential decline. So the curve is actually going up, but it's going up at slower and slower rate. And this happens when a is less than 0, so it's negative, and b is less than 1. And that's what our original formulation. So we still have the same formulation so far. And so we have here that it will be increasing, in this case, towards 0. So as we get to infinity, the curve will approach 0, but at slower and slower rate. Now, the obvious curve that we need is this one, increasing exponential decline. But we don't need it to be negative. So in order to not have negative values, we're going to add a new parameter called c to shift the whole the values upwards. So our now models become a times b to the x plus c. So that'll help shift the entire curve up. It's the same parameter over here for the continuous exponential model. So here we go. We're just going to have, we're going to just pick some numbers over here. We're actually going to pick two different growths, both less than 1 to show exponential decline. This will be increasing exponential decline because a is negative, but it will be, the values will be positive because now we're adding this c parameter over here. And you can see that we get that shape and the values are indeed above 0. Okay, so let's go ahead and put this model in. And now we have 3 parameters in our model, so we're creating a function that we'll be able to pass to predict all. So that's our whole purpose here, is we need to find that function. We need to define that function such that we can pass it to predict all. X always comes first, and then the parameters, which it doesn't matter how many it has, come next. So yeah, here's our initial value, B is still the growth rate, and C is now this new parameter of the vertical shift. Okay, so we have to give it new bounds. So we're saying A, the initial value, has to be negative. That's these first two. B, the growth rate, will have to be less than 1 if we're using this formulation, not the continuous version. And then C will need to be positive. We need to shift it up, so we're just giving it a very large range here. And then we're just gonna put in some initial values here for A, B, and C, and we're just gonna pass it like we now can do very easily to predict all. We now have our new model, and the shape does match this exponential decline. So here is our model, our predicted cases in orange. It's been trained on data before April 10th. So this is the unseen part over here. And we need to remove this to actually get the values of the coefficients. So this is our model over here. That's A, here is B, and here is C, and then here are the new daily cases, and as you can see that they are declining in value. Okay, so a little summary for all of the different variations of our exponential function. And I'll just go over the simple formulation. So A times B to the X. So increasing exponential growth looks like this, is when A is greater than 0, B is greater than 1. We have decreasing exponential decline. That's when A is greater than 0, but B is less than 1. Decreasing exponential growth, so we didn't cover this one. So A is less than 0, and B is greater than 1. So this is going to go off to negative infinity. So it's just the inverse of this one over here. And then increasing exponential decline, which is the one that we used here to model the tail of the coronavirus curves. That's when A is less than 0 and B is less than 1. And you get the same thing with the continuous summary over here. There's just a slightly different, instead of B less than or greater than 1, it is B greater than or less than 0. Okay, so we have exponential decline that models the tail of the curve well, and exponential growth that models the beginning well, going over here to Texas. So in the next part of the book, we're going to learn about a different model, a logistic model, that can sort of combine these two ideas and have exponential growth at the beginning and exponential decline at the end, so that it can fit these coronavirus case curves much better than any of these individual ones.